Yes, sir.
Yeah, okay. Um, Good morning, everyone. This is again the live interaction session for the NPTEL course Interfacial Fluid Mechanics. Uh, these sessions are primarily meant to interact with the instructor and give you direct feedback, take your questions and clarify your questions based on the content in the course. So whoever has joined, any students who joined the course, you can start with asking your questions.
Hello, am I audible? Sir, you're not audible still. Uh, Sir, I cannot hear you, sir.
Himanshu, can you still hear me? Can you hear me or not?
Hello?
Can you hear me?
Yes, sir. Now I can hear, sir. Now I can hear. Sorry, must have been some connection problem.
Okay.
Sir,
Yeah.
so sorry, sir. I wanted to ask about Wenzel state. So when you were writing in the volume for the Wenzel state, sir, you still wrote integral 0 to a 2 pi x h dx. So my question was that in Wenzel state, sir, we were having this values because of roughness in which the fluid was penetrating. So the volume would not still remain that 2 pi x h dx. It would change, wouldn't it?
Let me just open the appropriate lecture. This is on week 5. No, week 4, sorry. No, okay. Give me a second. I'm trying to. Give me a second, Himanshu. When you open up the appropriate one.
It is in week 5, sir.
Yeah, I know. I just have my OneDrive has changed on the system. I'm just trying to sort that out. Okay, I have that on my iPad. Let me just try and figure out where that is. Okay, or it's all right. So tell me, can you go ahead with the question?
Sir, when we were discussing about Wenzel state in the beginning only, so sir, you wrote the volume term. The volume of, so the constraint we were putting as lambda v. So for the energy functional, and this, sir, this volume you still wrote as integral 0 to a 2 pi x h dx, which was for the smooth surface. The volume remained the same for the smooth surface in the Wenzel state, but in the Wenzel state we had this valleys in which the fluid was penetrating. So strictly speaking, the volume would have been a little bit, different compared to. So my question is to so the argument is that here earlier we were saying that closer to the solid liquid interface is the most of the energy that we are interested in. So in the before also when you were talking about Young's contact angle, so the energy is closer to that surface. So now if we put an error inside the volume, uh, which is actually near the surface, so it would cause a huge error in the energy functional itself. So that is why it concerns me.
This is only okay, if only for a small volume, right?
But that volume is near the surface, right? So that is where the energy is.
Yeah. So the way to there are two questions to understand. First is okay. There are several things one has to keep in mind when we do these kinds of problems. For example, what is the baseline for a rough surface? Okay. For example, when you want, why do we need the baseline? Basically, we say there is a horizontal surface, flat surface. On the flat surface, I introduce a small roughness. So this is actually one way actually to set up an experiment as well. If I want to create a surface, you start off with a smooth, let's say glass surface, and then you can do an etching on the surface so that you can do etching or rub it with an emery sheet or a sandpaper. Okay. So that you create a controlled rough surface. Now the baseline for first you would need the horizontal surface. Why do we need the horizontal surface? Is because the horizontal surface is used as a reference to measure the angle. The challenge that you are telling about is one level higher, which is the volume. But the same question, if you think about it, is also arises when you ask, what is the angle? From where do I measure the angle? Okay. So the angle measurement also has the same issue. You need to first determine what is the horizontal surface. One of the most convenient ways to determine a horizontal surface is basically somewhere in the middle of that roughness. So you think of roughness as basically little crests and troughs, okay, hills and valleys locally. And somewhere in the middle of that is basically your reference. Okay. You can take it to be a little up or down, doesn't really matter. Somewhere in the middle is basically your reference. Now, using that reference, you measure an angle. Okay, so what is the angle that you see? This angle is not the angle exactly that the interface makes at the wall. This is the effective angle that you see. Okay, that's one. The underlying assumption here is that the roughness is basically very, very small compared to the scale of roughness is these kinds of theories. The scale of roughness is very, very small compared to the scale of the problem. In this case, the scale of the problem is roughly, let's say, take the droplet size, and the roughness scale is much smaller than that. In that scale, you are basically making a bunch of small approximations. What is the effective angle? Because that is the angle that you would see in an experiment. Every surface is intrinsically rough. Okay, any experimental surface, no matter how, unless you go, the best roughness you can get is atomically smooth. Okay, even that is basically only smooth up to an atomic scale. Mathematically smooth surface doesn't exist. Okay, so you're measuring an effective angle, which we've called it as theta star, and that is basically measured with respect to some effective horizontal, some approximate horizontal surface. Okay, and your volume variations that you're talking about with the crests and valleys will be accounted for. The volume variations will be automatically accounted for. Okay. So I don't think it should be an issue. I don't think it should be an issue. Okay.
Yes, it is. I was not knowing about this, like how to. So, sir, since you have mentioned this, you were also saying about like the apparent contact angle that we see in the experiment, and the contact angle that we see in the experiment and the apparent angle. So, are they the same, or I mean, is there any difference?
No, the theta star is what you would actually see in an experiment. So if you basically make the surface really smooth, then the theta star will approach theta E.
Yes, sir. Now got it. Sir, there is one thing regarding the convention itself. So when you were writing the energy function earlier, so in the energy function, so you were writing E, so that you were writing like J you were representing, and equals to integral F. So F was a function of X, H, and Hx. So in that you were writing that within that F you were writing the volume itself. the lambda v,
Yes.
minus lambda v term.
Yes.
But later on in the week 5, when you wrote a j equals to integral 0 to a, and then you wrote the FW term, like the Wenzel term, and then you wrote the volume term, the plus lambda times the volume term as separately, the constraint. And then you were representing the j as f and other constraints separately. So my question is, as to in the convention, are you taking the j, which is the energy, as complete with the constraint, or you're separating the constraint?
So if I recall correctly, you see, you can introduce the constraint. I've introduced two functions here, f and fw. Okay, correct? So
Yes,
for example, if you look at week 5, the so-called, there's a discussion on the so-called Wenzel model, correct?
Yes, sir.
So if you look at the Wenzel model per se, basically I have wait, give me a second. Maybe I'll just try and is there a way for me to project this? I'm trying to see. For some reason, it didn't get updated here on my laptop. I have an older version of the OneNote files. Okay, give me 1 second. I'm just trying to find that out. This is week 5. Just bear with me for 1 more minute. Yeah, thanks for bearing with me. So I'll just open the necessary thing so that we can discuss this more clearly. Can you see my screen now?
Yes, sir. It is visible.
Okay, so let me just open the necessary portion of this. This is basically the general discussion on wetting on rough surfaces, wetting on textured surfaces. We are of the Wenzel model. That's where we are talking about, right?
Yes, sir. Yes, sir. It is, sir, above. I mean, a little bit above. Sir, so in the Wenzel state, down there you wrote that complete term as F. That complete term was written as F in the in this formula, which is written below here. Yeah. And here, sir, here it is written F equals to plus lambda term. This is here.
Yes.
But above, sir, above when you scroll, when you have written FW. So this FW. Yes, sir. Here, so here there is no volume term.
So that's what I have written down. If we impose an additional volume constraint, the way to do this is you can introduce it in J, in F. Sorry. So the first one, if you look at this expression here that I have written down, where I'm pointing my mouse, okay, you can notice that I have not imposed any volume constraint. Okay.
Yes. Yes.
I have introduced an external field that is capital U. Okay. It could be most common external field is typically gravity. But if we want to introduce an additional volume constraint, then we introduce that external volume constraint with the help of this parameter lambda, which is the Lagrange multiplier. Okay. Is that clear? So you can actually try and ask this question: what is the minimal shape on a rough surface for a given volume? Okay. So here I'm just saying this is my functional, this is my constraint. Okay. And therefore I basically get I'm only interested in what is happening at the corner. That comes out of the boundary term. If you've gone through the Lagrange multiplier discussion, that only the boundary term will reduce to something like this.
Yes, sir. Yes, sir. It is there.
Okay. And from which we get a expression like this. So we say that the effective angle theta star is related to the Young's angle through this roughness parameter R. And this tells us that surfaces which are hydrophilic to begin with become more hydrophilic if you basically just roughen it. Of course, you have to keep in mind that the roughening process should not change the wetting characteristics of the surface for the statement to be valid. Okay. So for example, I take a hydrophilic surface and I chemically treat it to let's say I etch it. Okay, chemical etching I can do it. Then in the process, I should not coat a thin layer of some other material on the surface, some other deposit on the surface, which changes the wetting characteristics. If I don't do that, then the surface becomes even more hydrophilic. The same applies for hydrophobic surfaces. This is just a direct, it directly comes out of this math, which is cos of theta star is R times cos theta y. We have one more student as well. Purna Sai, Samudrada Purna Sai. Yeah, good morning. I can't hear you because you're muted. Should I call you Sai?
Sir, good morning, sir.
Good morning.
Hello?
Yeah, I can hear you, Sai.
Sir, good morning, sir.
Very good morning.
Sir, here I have a doubt on how the volume, that means how we relate, if we take semicircle, how we relate the height h and r field and the contact angle.
So if I take a what again? Let me understand your question. If I just take a semicircle.
Yes, sir. If I take it, that means in this slide itself only, I think there is a diagram of that. Yes, sir. Here.
Okay.
In the Vision model, if I take the height of this semicircle as h and radius of this as RC, and how we find the relation between HRC and contact angle theta y.
Okay, so the question that you are basically asking me is inherently connected. I mean, let's consider. Are you first of all suggesting that when you say radius is RC, you are of the droplet, you're inherently saying that it is it is part of a sphere. Is that correct?
Yes, sir. Yes, sir.
Huh?
Yes, sir.
So if you go to in the next lecture, there is a discussion on alternate approach. Did you look at that?
Yes, sir.
Can you open that? Can you open that discussion? Let me also open that file and share it on the screen. Are you there, Sai?
Yes, sir. I am here.
Okay, so I'm just sharing the screen. You can take a look at it. So this is of course only a special case because it's what is called as referred to as a spherical cap approximation. Yeah, so you can clearly see in the spherical cap approximation, we are only interested in doing this only for cases where there is no gravity, because when gravity is absent, a droplet, basically the minimal shape of a droplet, the minimal energy state is directly the state where the surface area is minimized, because there is no other energy apart from surface energy, and the surface area is minimized for when the droplet assumes a spherical shape, okay, or rather a part of a sphere. Okay, in this case we call it a spherical cap approximation. I've specifically mentioned here that there is no gravity here. Okay, so let me highlight that bit here. It's specifically there's no gravity in this region. Okay.
Yes, sir.
Now, in the spherical cap approximation, what you're essentially, I've already given this is just direct geometry. You have radius is R,
Yes, sir.
radius of the droplet is R, and the projection of the droplet on the flat surface is A. Projection is basically the surface, the wetting surface on the horizontal surface is A, which can be directly related to the radius R as A equals R sine theta. And now you can actually write down the expression for the volume and the surface area. Note that this is the volume only of the spherical cap, not the entire droplet. Okay. And the surface area is only for the surface area of the upper surface. This is the surface area of the liquid gas interface.
Yes, sir. Sir,
So
here, sir, here A equal to R sine theta. This is also an approximation of A, no, sir.
This is not an approximation. This is just geometry. This is exact.
Here, from the geometry, that means here theta means here contact angle, no, sir.
Yes.
Okay. Okay, sir. Okay, if this is okay. Okay, sir.
Okay, so this is not an approximation. This is exact.
Okay.
Okay.
Okay, sir.
There is no approximation in this particular result.
Okay.
Yeah. Oh, is that clear?
Yes, sir. Yes, sir.
I believe I have discussed this a bit earlier as well. I'm just trying to pull out the exact notes where we did this. So earlier I've done the same thing for when we've done the Young's law, but for the very first discussion of Young's law was also done in the same way. Okay, so there is a bit more discussion. Let me. Can you look at
The partial wetting, sir. Wetting.
no, can you look at in week 4, there is a discussion on the Young Laplace equation. Let me open that. Yes, partial weighting. Okay. So let me just share the screen now, this part of the thing. Can you see this?
Yes, sir.
Yeah. So this is partial weighting. Again, you see, this is first. I've done this first for a spherical cap, and then I have extended this to an arbitrary surface. Okay. Where I don't necessarily have to assume that it is part of a sphere. So we can introduce gravity and so on. Again, the same ideas come in. So theta E is here. I've called it this RC is basically wetting surface. There I've called it A in the subsequent lecture. Here I've called it RC. Okay. RC is directly related to the angle theta E at this location. Okay. And theta E, as I said, is the contact angle. There are, of course, other ways of writing it. Theta E is written sometimes because it's referred to as the equilibrium angle. Theta Y is because it's a Young's angle. Theta S is because it's the static angle. Okay, for us, all of them in this particular case are all of them are the same. Okay, again the same idea. The height is related to the height at any given location is related to the radius and theta E. Okay. The wetting surface again is written in the same way. The volume expressions for the volume are given. The expression for the volume for any height and wetting surface is also written like this. This is just coming from geometry. Okay. I don't know if that answers your question.
Okay, thank you, sir.
Yeah. So are you able to follow the lectures and the assignments?
Yes, sir.
Okay. All right. Okay, good.
Thank you, sir.
Nice to interact with you, Sai. Please do. I'll be there almost every Saturday. The first 2 weeks, we started this, I think, from the 3rd week. So the plan is to have this interaction every week so that if you are able to follow the lectures, spend the week looking at the lectures, and then over the weekend, you please bring your questions so that we can have a direct clarification on the material. Okay.
Thank you, sir.
Yeah. So if there are no more questions, can we end the session? Himanshu, do you have any questions?
Sir, just one clarification, not a question, but so when we were discussing about Cassie-Baxter state model, and in that we had this patches of different surface energies at the solid surface, and so yes, sir, like this checkerboard. So, but we were saying that every patch has a associated different surface energy with it.
Yes.
So, sir, so how are we guaranteed that the contact angle theta would be the same across all the patches?
It is not.
Because
it is clearly not.
But sir, when we did the analysis, so when we wrote for the cos theta star, so the theta star, when we wrote the apparent angle, we had only one single apparent angle coming out. It
yes,
was
so that's why we call it an apparent angle. That's precisely why we call it an apparent angle. So let's imagine this, that the entire surface, here I've shown the different colors that you see here. Now this checkerboard pattern, the colors are slightly different. They are, if you notice, they're not exactly the same shade of gray. The idea is to state that I'm trying to convey the information that these are surfaces where on each square, the surface energy can be assumed to be constant, but it is varying. This is just a simple model, remember. That's why, in fact, I call this a Cassie-Baxter model. Okay, so the idea essentially is that how do we reconcile the fact that surfaces can have chemical heterogeneity, and yet an effective angle emerges for such a surface. Okay, in reality, of course, just like the roughness case, the size of these little checkerboards that you see have to be really small. Each square has to be really small compared to the size of the droplet. Okay, depicted by an effective radius A, or a radius A, right? Radius R or radius A, whichever radius you can think about. Okay, this is only an effective angle. Okay, so if you zoom in microscopically, if you're able to basically measure the angle where the contact line meets each surface, there locally the angle will be slightly different. You understand? There will be a little adjustment of the surface. For example, where the surface here, if the surface meets, let's say, one of the light gray surfaces, the local angle is slightly different from when the interface meets one of the dark gray surfaces. The local angle, the equilibrium angle, or the Young's angle is slightly different at each locations. From that, an effective angle emerges.
So here also we have this meandering thing that you were talking about there in the.
Absolutely. Just like in the case of a rough, if you take a rough surface, what really happens on a surface, in reality, what happens is if you do an experiment where you put a droplet and look carefully at the contact line, let's say from above, what you will see is that the contact line is not a perfect circle as we would draw on a piece of paper. It won't be a perfect circle, but there will be little undulations on the surface. Okay, so one of the ways that one of the reasons why you have little undulations is because either the surface has small roughness elements, which means that locally the angle, the interface is still maintaining the Young's angle locally at the level, at the scale of each ridge, but macroscopically it is approximately a circle. Okay, and we are basically, what we are essentially trying to do is account for this in some approximate sense. Okay, now when it comes to the same argument can be extended to surfaces where there is chemical heterogeneity. Locally, this again will lead to a contact line which is not a perfect circle but slightly wavering. Okay, it will be slightly rough. The contact line will be slightly rough, and this rough contact line is associated, can be thought of as being associated with small undulations, small variations in the angle as you go from one element to another element on this chemically heterogeneous surface.
Now I get it. Now, just out of curiosity, I wanted to ask. So in the Cassie-Baxter model, you said that we could have chemical treatment of the surface, like the patches. You can. Is there any way in which we can change the surface energy and not treat it chemically, or I mean, so change the surface energy at a patch, but without changing the chemical chemistry of the surface? Is there any method of that? Can we do it?
I mean, unless you make your surface itself is a composite surface. For example, you could have a surface which is a composite surface. let's say you could have surfaces like that. It is inherently a composite surface. Like for example, you basically I don't know, some kind of a complex alloy where you basically you have each of these patch is let's say polycrystalline material. This is of course a speculation. I can't have to look up whether this is actually true. But if you take a polycrystalline surface and then you basically smoothen it, make a flat surface, what the contact line sees and within each grain is basically one material, let's say. But then as you go to another one, when you cross the grain boundary, you have, let's say, another crystal. Or that could be one possibility. Okay, I really don't know. But usually what is, it is possible to make surfaces like this, exactly what I've shown. What essentially is done is chemical treatment is done. But what you do is you cover the part of the surface which you don't want to react. Okay, so you cover it, you protect that part of the surface. That the word that is used for these things is, it's called a mask. You apply a mask and then you basically do chemical treatment so that the part of the surface that is exposed, there the local surface energy changes, and then you can repeat this process to generate as complex surface as you want. So it's very common for people to produce chemicals, the chemically heterogeneous surface in the form of the easiest one is basically produce strips, vertical strips or horizontal strips where the local contact angle is different.
Yes, sir. No, I understand.
Okay. Okay. So if there are no more questions, then can I request the NPTEL team to stop the live streaming, and then we can meet next week again. Okay, thanks to the students who participate. If those of you who watch this live stream later, I encourage more of you to join, and we'll meet again next week.
Thank you, sir.
Yeah, thank you. Thank you, Sai. Thank you, Himanshu.